I captured this picture out of your book. It's on page 122. This section in chapter 3 is tangents and the derivative at a point. We have not really defined a derivative, but we have looked at slopes of secant lines, and I've kind of given this away, that the slope of the tangent line is going to be the derivative. See, the slope of the secant line here is the slope of this line, right? And how we came up with the slope of that line was by using, the change in y, f of x sub naught plus h minus f of x sub naught divided by h. That's how we came up with the slope of this secant line, where here's the change in y and here's the change in x. It's that distance h. Well, as we let this point Q slide closer and closer and closer to P, this secant line is going to become this tangent line, right? Do you see that? So that we can end up saying that the limit as h goes to 0 of the slope of the secant line is going to be the slope of the tangent line. As h gets smaller and smaller, this point right here is sliding closer and closer to x sub naught. Do you see that? So as h gets smaller and smaller, we're talking about a limit, aren't we? When things get smaller or approach something, that's the concept of a limit. So what we end up with then is this formula. The slope of the tangent line at any point is going to be the limit as h approaches 0 of the change in y over the change in x. The change in x is going to be this distance right here. This happens to be a derivative. They haven't called it that yet, but this is a derivative. The slope of the tangent line, I've given away the ending, is the derivative. Okay, that's our first calculus-y word. Well, limit, I guess, is 2. Okay, so the slope of the curve at a point P, where the x value is x sub naught, is the number m, where it's the slope of the tangent line. The tangent line to the curve at point P is a line through P with this slope. We've done these type problems before, writing equations of tangent lines, haven't we? Sure we have. Once we found the slope of the tangent line, we can write an equation. All right, so in example 1, we're asked to find an equation for the line tangent to this line at this point. In order to write an equation of any line, you need 2 things. What 2 things is it that you need? To write an equation of a line, we need a point and a slope. Well, the slope is going to be this limit right here. The slope of the tangent line, according to this definition, is going to be the limit as h approaches 0 of f of, in this case, it's negative 4 plus h minus f of negative 4, all divided by h. That gives us the slope of the tangent line. Any questions about that so far? Nope. Our function is negative 3 minus 3x squared. Are we ready to find the slope of the tangent line? We have our point, x and y. We're okay with that. So let's find the slope of the tangent line now. What is this going to be? This is going to be the limit as h approaches 0 of negative 3 minus 3 times x, not x, negative 4 plus h squared minus, yeah, that's the x value of the point. Yeah, when you look at this formula right here, here's your point, and the x value of the point is what you plug in here and here. Does that help? I'm glad you asked. So that x value, or x naught, is negative 4. So that's what we plugged in here and here. So now we do minus. Now we need this value right here. And that value right there is going to be negative 3 minus 3 times negative 4 squared, all over h. So far, so good? We're just using this formula. Okay, we replaced x of naught with negative 4, what we said it was equal to, and then we plugged that into the formula right here in place of x. Now we've got to clean it up. We've got a lot of algebra to do here. So this then is going to be, as we start cleaning this up, this is going to be the limit as h approaches 0 of negative 3 minus 3 times, when we FOIL this out, that's going to give us 16 minus 8h plus h squared minus times, okay, negative 4 squared is 16 times 3 is negative 48, 49, 50, 51. Yeah, that's negative 51. And when you subtract a negative 51, you get positive 51. This is now going to be the limit as h approaches 0 of negative 3 minus 48, because I'm distributing this negative 3 here, right? By the way, you had to FOIL this out. That's where this came from right here. You see that? So let's go back. Negative 3 minus 48 plus 24h minus 3h squared plus 51 all over h. Well, negative 3 minus 48 is negative 51, isn't it? So this is going to cancel out with these. Do you agree? And then that leaves us a common factor, doesn't it? So this is the limit as h approaches 0 of h times 24 minus 3h all over h. Our common factors will cancel out then. And we're left with the limit as h approaches 0 of 24 minus 3h. And what is this equal to? 24. Guess what this is? The slope of the tangent line. So the instructions here were to write an equation of the tangent line. So to write an equation of any line, we can use y equals mx plus b. What are we going to plug in for y? Negative 51. What are we going to plug in for m? What do we plug in for x? Plus b. So this is negative 51 equals negative 96. Is that right? All right, so then to move that over, we're going to add 96 to both sides. So then that's going to give us b equals, so the equation of the tangent line is y equals 24x plus 45. There's the equation of the tangent line. The slope we got from looking at this limit. The intercept we got from using y equals mx plus b. The only thing you need to write an equation of any line is a point and a slope. Next, look at these tangent lines at these various points. Do you remember increasing, how to tell if a function is increasing or decreasing? You read a graph like you read a book, meaning from left to right. So moving from left to right, if the graph is going down, then we say that this is a decreasing. Decreasing functions have negative slopes. Now, the more horizontal this tangent line becomes, the tangent slopes steep near the origin become more gradual at the point of tangent C as they move away. What happens is, the larger this value is for the slope of the tangent line, the more vertical the line is. The closer it is to 0, the more horizontal the line is. Let me write that out because it's probably worth noting. The larger the absolute value of the slope of the tangent line is, the more vertical the line is. The more horizontal, the closer the slope of the tangent line is to 0. Horizontal lines have what slope? 0 slope, right? Vertical lines have an undefined slope, and that's because you're dividing by 0, which means it's going off to infinity or negative infinity. Now here's 2 points, 2 different points on the graph of this function y equals 1 over x that actually have the same slope. The equations, though, of these tangent lines would have two different y-intercepts. So that's how you can tell that they're two different equations, even if they have the same slope. Okay, the derivative. Okay, we finally get to it. The derivative of a function at a point is the value of, isn't this limit what we just used to find the slope of the tangent line? This right here is what we just used to find the slope of the tangent line. That's why up here, I told you the slope of the tangent line is the derivative. I gave it away because I knew eventually we would get here. Now, we have a bunch of different notation for derivative. This is one type of notation. Let me write this down, because this, I didn't realize, I was tutoring a student at Baylor when I was in grad school. He didn't understand the fact that this, they all mean the same thing. It means find the derivative with respect to x. That's different notation for the same thing, the derivative. You may ask yourself, well, why do we have all this different notation if it all means the same thing? I don't know. I have a feeling what happened is before the internet, people still were smart and they were still working, and they were working independently. And in India, in the 1600s, 1500s, some guy came up with this concept that we discovered was called calculus. Whenever the French and the Germans got together, they found out they had people that were working with calculus. Newton was working with calculus, the English, the French, the Russians, the Indians, everybody, and they all had been working in their little isolated groups, but because they didn't travel that far or that often, they didn't have an opportunity to share on a regular basis with their colleagues. So when they got together, these guys all had their students. They had taught them their methods using their notation. In America, we're a melting pot, so we just adopt everybody's notation. We don't care. So we try to be all-inclusive. So we took everybody's notation and blended it in and said, okay, this is what we're going to call a derivative. Depending on the author of the book, they tend to lean more to one form as opposed to another. But there's a whole bunch of different notation that we can use for derivatives. You need to know it all. I'm kind of partial to the y prime because it's less writing. Oh, there's another one that's very common. dy over dx. That means the derivative of y with respect to x. And that's probably the one that you're going to see the most. So I should have written it first. All right, example 2. An object is dropped from the top of a cliff 630 meters high. Its height above the ground t seconds after it's dropped is this. Determine its speed 4 seconds after it's dropped. Have we discussed velocity at all yet? No. Okay, well, here's what we need to know. There is a common set of notation that we use here. S of t is what we use to give the position of a function. So S of t here is 630 minus 4.9 t squared. So this is the position function. V of t is what we use for the velocity, and that's going to be the derivative of the position function, and this is velocity. Position is where you are, velocity is how fast you are going. So what that means is, based on this derivative function, we're asked to determine the speed, that's the velocity, after 4 seconds. So t is going to be equal to 4. What this means right here is we want to find the velocity at 4 seconds. So I want to find the derivative of this position function when t is equal to 4. Do we know how to find derivatives yet? Yeah, it's that slope of the tangent, the secant line, or actually the slope of the tangent line. We can do this. So let's do this. This is all background information. So S prime of t, let's use 4, is equal to the limit as h approaches 0 of S of 4 plus h minus S of 4 all over h. Okay, so replace the name of the function with what the function does. This is going to be the limit as h approaches 0 of 630 minus 4.9 times 4 plus h squared minus 630 minus 4.9 times 4 squared all over h. Any questions about how we got anything up here? Got to make sure you can follow the algebra. So this is going to be 630 minus 4.9 times 16 plus 8h, plus h squared minus 630 plus 4.9 times 4 squared. Now let's say 4.9 times 16. All over h. This is a really big number, and I don't care to find it because I know that once I do finish the foiling and distributing over here, I'm going to have things cancel out. Any term without an h is going to cancel out if you perform FOIL correctly. So that way you can cancel out that h in the denominator. So this is going to be the limit as h approaches 0 of 630 minus 4.9 times 16 minus, what's 4.9 times 8? That one I need. H minus 4.9h squared minus 630 plus 4.9 times 16 all over h. Now here's where the fun happens. Things are going to cancel. There's a 630 and a negative 630. There's a minus 4.9 times 16 plus 4.9 times 16, which means that the two terms I'm left with on top here both have a common factor. And if you do the arithmetic correctly, you will always have a common factor in the numerator. You've got to, because that factor has to be canceled out with the h in the denominator so that you can evaluate this limit. So this is negative 39.2 minus 4.9h all over h. Now these h's are going to cancel, and we end up with what for the limit? What were we asked to find again? What does this number represent? Velocity. Determine its speed. Okay, this is the velocity. Velocity has direction. The negative means it is going down. Speed, though, is the absolute value of velocity. Speed is just how fast it's going. So there's something else I should have told you up here, that the speed is equal to the absolute value of velocity. So this is going to be then the speed is equal to 39.2 meters per second. The velocity is down 39.2, or falling 39.2 meters per second. Any questions?
What about, is the negative sign just indicating that it's...
The negative sign indicates the direction. It's like a vector. It's showing that it's going down. That's why I said speed is the absolute value of velocity. I didn't want to know the direction, I just wanted to know how fast. Now, if I would have asked the question, determine its velocity, I would have wanted the sign with it. I would have wanted the negative. The following are all interpretations for the limit of the difference quotient. That's what we call the slope of the secant line, by the way. It's the slope of the graph of y at x equals 0. It's the slope of the tangent line to the curve at the point. It's the rate of change with respect to x at x equals x and naught. It's the derivative at a point. These are all of the things that a derivative is, or the slope of a secant line. This is what calculus is about. All of these, this limit right here represents all of these. Different names for the same mathematical operation, but it's all these different concepts. And that wraps up this section.